Welcome to The Explainer. Today, we're digging into the most critical, unsung hero of generative AI. It's not the flashy algorithm or the complex code. Nope. It's the one thing that can sink your entire project before you even get started. So, when you think about what makes an AI really powerful, what's the first thing that comes to mind? Probably some super complex algorithm, right? Or maybe a room full of massive humming servers. Is it all about having the most sophisticated, state-of-the-art model? Well, that's definitely a piece of the puzzle for sure, but it's not where the story begins. In reality, the true magic, the absolute foundation of any great AI, starts right here, with high-quality, well-prepared, and deeply understood data. Okay, let's kick things off with the one, unbreakable, golden rule of all machine learning. Garbage in, garbage out. It's simple. If you feed a model messy, inconsistent, or just plain bad data, you are absolutely going to get messy, inconsistent, and unreliable results. There are zero shortcuts around this. So before we can even dream of training a model, the very first step for any data scientist is something called exploratory data analysis, or EDA for short. This is where you put on your detective hat. Think of EDA as a full-blown investigation. You're sifting through your data, looking for clues, trying to really understand its personality. Its strengths, its weaknesses, its hidden patterns, and all its little quirks. This whole detective phase is all about setting the stage for what comes next. It helps us spot the obvious problems right away, like missing information or totally wild outliers. But even more importantly, it helps us uncover the sneaky issues that can poison the entire project, like unbalanced data. And this is a huge deal. Seriously, let's say your dataset has 10,000 pictures of cats, but only 100 pictures of dogs. What do you think is going to happen? The model becomes a world-class expert on cats, but it's completely unreliable with dogs. It just learns to favor what it sees most, which can lead to it failing on those rare but really important examples. Okay, so our detective work has turned up some problems. Now it's time to call in the cleanup crew. This is where we roll up our sleeves and actually turn that messy data into a reliable, trustworthy asset. This is the essential, gotta-do-it, dirty work of data science. We're filling in the gaps where information is missing, we're getting rid of duplicate entries that could totally skew the model, or fixing annoying inconsistencies like having 5 different ways to write the same date, and crucially, we're dealing with outliers. Spotting outliers is absolutely critical. Using some statistical methods, we can mathematically identify the data points that are just way different from everything else. If we leave these in, they can pull the model's attention in a completely wrong direction, forcing it to learn patterns that aren't really there and generate some pretty unrealistic stuff. But here's the fascinating twist. You can't just delete every outlier you find. Sometimes that one weird data point is the most valuable piece of information you have. Think about it. When you're detecting credit card fraud, the fraud is the outlier. In medicine, a rare disease is the outlier. In those cases, the outlier isn't the noise, it's the signal you're looking for. So, our data is now squeaky clean and reliable. Great. The next step is to translate it into a language that the model can actually understand and process efficiently. This is where we get into all the formatting and encoding. So here's a crucial point. We have to put all of our numbers on a level playing field. It's called normalization. By scaling all of our numeric values to a consistent range, like, say, 0 to 1, we stop features with huge numbers from unfairly dominating the learning process. This makes the training faster, way more stable, and in the end, gives you much better results. All right, but what about data that isn't a number to begin with, like text labels or categories? Well, we have to turn them into numbers. A couple of common ways to do this are one-hot encoding, which is awesome for categories that don't have a natural order, and label encoding, which works perfectly for things that do, like, small, medium, large. But for something as complex as human language, for that, we need something way more powerful: word embeddings. And honestly, this technique is a total game changer. Instead of just giving words a simple numeric label, it translates them into these rich numerical vectors that actually capture their meaning and how they relate to other words. This is exactly why embeddings are so revolutionary for text generation. They let a model understand that king is to queen in the same way that man is to woman, or that happy and joyful are semantic neighbors. This deep contextual understanding is the real secret behind AI that can write coherent, human-like sentences. So, Our data is now perfectly prepped, but how do we actually use it to build a model, especially at a large scale? Well, for that, you need a specialized toolkit, which is where a powerful framework like TensorFlow comes in. Now, a lot of data scientists use standard tools like NumPy, but TensorFlow is a completely different beast. For one, it's built to run on specialized hardware like GPUs, which can crunch the massive calculations needed for AI way faster than a regular computer. And it has this built-in superpower called automatic differentiation, which is basically the engine that allows a model to learn from data during training. TensorFlow also gives you this incredible flexibility. When you're developing, you can use a mode that runs everything line by line, which makes it super easy to experiment and debug. But then, when you're ready for maximum speed, you can switch to a different mode that pre-plans the entire computation and optimizes it to run as efficiently as possible. It's kind of like having both a workshop for tinkering and a high-speed assembly line all in one toolkit. So, let's put all these pieces together. We've explored our data, we've cleaned it, we've transformed it, and we have our powerful tools ready to go. Let's take a look at the entire journey, from a messy raw file all the way to a trained generative model. You know, the whole journey really boils down to this simple but absolutely critical pipeline. First, you pre-process. That's all the cleaning and formatting we just talked about. Next, you visualize, which gives you one final chance to eyeball everything and confirm your data is solid. And only after those two steps are completely done do you finally unleash the data on your model for training. And this brings us right back to our main idea. The most important thing to take away from all this is that the success of a generative AI model isn't really decided during the final training. It's forged much, much earlier, in the meticulous, sometimes painstaking work of data preparation. That isn't just a step in the process. It is the foundation. Which leaves us with a really fascinating thought to chew on. Data preparation is by far the most time-consuming part of building an AI today. So as these models get more and more intelligent, will we ever reach a point where an AI can learn to reliably clean and prepare its own data? And what would that even mean for the future of building AI?